My talk is what everyone should know about how amazing compilers are. And hi. I've already been given a bit of an introduction by Phil, but realistically, this is the best way I can introduce myself. I'm accidentally a verb. I didn't mean to become a verb, it was not planned. I think most of you know about this website, which now is becoming less and less my website and more a collaboration between a bunch of us. But it was born in 2012 when I was discussing with a colleague about whether or not we could adopt these fancy new features that were coming in C++, like range for and things like that. And there was a difference of opinions because not in other languages, range fors have not always been free. They've been, they're behind the scenes, things get created and destroyed, iterators and whatever. I'm talking mainly about Java if you've looked into it. And working as I was then for a high-frequency trading company, every sort of nanosecond counted. So there was a really kind of sense that we should understand what we're doing. And so while we were discussing backwards and forwards, I ran a little shell script. So I don't know how many of you use Unix, but there are some fantastic ways you can kind of pipeline together commands. And so I ran watch, which is a program which executes whatever the arguments it's given as another command, and then it keeps running it every 2 seconds and showing you the output. And I did watch GCC minus capital S, some file name, and then I piped the output through C++ filter and some awk and some grep and some Perl to get rid of all of the nut stuff I didn't care about, and I hit return. And what I got was, every 2 seconds an updated disassembly view in ASCII in a terminal, but nonetheless. And then I split the terminal and I ran VI on the other side, and I was tinkering with code to sort of prove the points of what happens when we change things? And in that moment, Compiler Explorer was born. Although I had to go and make it all web because that's what the cool kids do these days. So the point of this talk, though, is to really just tell you how amazing compilers are. There have been so many great talks during this this conference, but there have been themes of the language is a little bit too complicated, or this is hard to parse, or how do we teach this, which are all incredibly noble things to talk about. But behind the scenes, the one thing that allows us to do what we do are the compilers, and I don't think we appreciate them enough. What is a compiler? Now, this has many answers. I know you probably think you've got your own idea about what a compiler is. A compiler takes some amazing high-quality code such as this and turns it into the very much underrated Xbox and PlayStation 2 game SWAT Global Strike Team. And what I mean by that is a tool for getting something done. You want to get something done. You've written some C++ to achieve a goal, and the compiler is the step between your code and getting that goal. More often, I write code like this, or a bit like this. Notice there's no, I use different names here for my silly objects, and what the compiler does is it takes that code and turns it into this, and this obviously is a much smaller version of the full error list. And that's why I'm not usually allowed to write templates. I would like you, at the end of this talk, to look at your code and look at the output like this and go, wow, a compiler is a tool for turning my C++ into poetry. All right, maybe not poetry, maybe more like Shakespearean poetry. The kind of stuff where you pretend you like it, and you read through it, and your eyes glaze over a little bit. You get the gist of it, and at the end, you're like, actually, that was pretty good. So bear with me. So yes, assembly, it's scary. I'm sorry. To many of you, how many people actually, I know obviously if you're using Compiler Explorer, you've probably been seeing a bit of it, but how many of you actually would say you're confident in assembly language? Okay, that's maybe a third, maybe under a third, a quarter. Well, you guys can fade out. You folks can fade out for a minute. But to the rest of you, perhaps assembly looks more like this, which is what's the inscription on the one ring, which I did try and memorize before this, but I'm a failed geek if I can't even say it. So I'm going to be talking about x86-64 assembly. There's just going to be a few slides of it because I want you to get enough of an idea so that the rest of it makes sense to you. And again, there's no tests. You're not expected to understand it completely. You've got to be able to glaze your eyes over and see what's going on behind it. But by show of hands, who uses 64-bit x86 as their sort of target architecture? Okay, that is the majority view. That means that what I'm about to say is not completely useless. The rest of you, presumably ARM is a target that you're going for. Is that right? Is there? I think there was someone who used there was another architecture that came up in a conversation earlier. But is anyone using anything more esoteric than those two? No. Cool. Right. ARM and x86 have it. So I'm going to talk about x86-64 just because it's the thing I'm most familiar with and it's the default on Compiler Explorer. And each of those lines of assembly looks something like this. It's either an instruction or an instruction with a destination operand or a destination operand and some number of source operands. And just before we go any further, there are two ways of showing this. This is the Intel syntax, or the correct syntax, as I like to call it. I'm sorry, that's such a trolling comment, but no, the destination is on the left-hand side. If you're used to AT&T syntax, it's exactly the other way around. So I like to think of it as dest equals source or whatever. But this is the general form of those instructions. Here are some example instructions. A 0 operand instruction would be like a return. 2 operands is like an increment of a particular register or a move of a value into a register. Adding takes 2. And one thing that's noteworthy in x86 is that the vast majority of operations have 2 operands, which means that they're usually destructive in some way. So like, an add takes 2 operands, so it's adding something into an existing value and then updating that value. So it's more like a plus equals than a plus, which is a little bit annoying because it means you lost one of the inputs, but compilers have to work around it. And then the newer ones, the newer instructions like this VP add, that one can have 3 operands, and that means that it's an operation of YMM equals YMM plus YMM2 plus YMM0. But we'll talk about those in a minute. These are the 20 most common instructions. I just took a random program, the program I run the most, which was node.js. I'm so sad. And I did a static analysis with some sed and awk and grep and objdump. And these are the top 20 instructions. So if you understand these, you understand pretty much all the instructions you'll ever see. And then the ones that you don't understand are the interesting ones that you can plug into Google and work out what they are afterwards. So we've got a group up here, mov, and liet. I'll stop pronouncing them now. These are all move instructions. They move either information between registers or information to or from memory, and they may 0 extend or sign extend. So the processor itself has no idea whether or not the values you're dealing with are signed or unsigned, but the choice of instructions that you pick, or the compiler picks on your behalf, determine how the sign bit is interpreted. So sometimes if you're reading a single char out of memory and you need to read it into a 64-bit register, you might want to sign extend it because you're taking a character and reading it into a 64-bit signed integer, for example. And LEA, we'll talk a little bit later. We've got call and return, which means go into a function, come back out of a function, jump to move around inside a function, push and pop to manipulate the stack, some comparisons and tests, and some conditional jumps, so you'll compare, and then maybe if something is true, you'll go off to a different part of the program. And then these are the top arithmetic instructions, so adds, exclusive ORs, subtracts, and shifts. Shul, short, and sar. I said I'd stop doing this. So shift left, shift right, and then shift arithmetic right. Again, that's that sign distinction between a signed value, where if you're shifting down a signed value, you want the signed bit to kind of stay at the top and smear down as you go. There are, of course, many more, and I mean, that's not even a joke. If you actually get the manuals, they're about this thick if you put them down, and they're growing all the time. They're adding new instructions like crazy. So those are the instructions, and I sort of said with the operands. What are operands? Operands can be registers, which we'll talk about again in a second, or constants, or something to do with memory. And this is where like the syskiness of x86, I mean, you've probably heard that CISC versus RISC wars of like the late 90s. This is firmly on the side of CISC. These are complicated instruction set computers. In that bottom size per to register plus offset plus register 2 times 1, 2, 4, or 8, we can do a single instruction like this, which says, I want to do EAX plus equals whatever I get if I dereference the memory at RDI plus 12 plus RSI times 4. That would be about 3 or 4 instructions on an ARM or any other sort of register transfer machine. So we've got quite a lot of complexity packaged in here, and that's a single instruction. Doesn't mean to say it takes one cycle or anything complicated like that, but that's a single instruction. So there's a lot of power in the way that we can express and refer to addresses in memory. Registers. So there are 64-bit general purpose registers. They're called racks, RDI, RSI, RDX, and other funny sort of names until we get to the R8 through R15, where apparently they gave up trying to come up with more complicated names. No, realistically, AMD, who came up with the extension for 64-bit architectures, also added in 8 more registers, and they just thought, well, we've had enough of this. Let's just call them something reasonable and rational. The thing you should really know about these is that they are 64 bits wide, they're general purpose for the most part, and if you're reading code, the return value of a function will be put into RAX by the end of the function body, and the parameters are passed in. The first 3 are in RDI, RSI, and RDX, and I can't remember what the 4th one's in, because who writes functions that have more than a couple of arguments, right? Yeah, you can look it up. And it's also worth saying that this is for Linux. Microsoft have a slightly different ABI, but you can look it up. Because this is sort of a legacy architecture, RAX is a 64-bit register, but you can still talk to the computer as if it was a 32-bit version, you know, some 10 years earlier. If you talk about EAX, EAX is a 32-bit register, which is also the A register. This is all like the A register, really. And if you talk about EAX, you're just talking about the bottom 32 bits of RAX. And if you're talking about AX, you're talking about the bottom 16 bits of RAX. And if you're talking about AH and AL, you're talking about these bytes down here. Now, this goes back to like the Z80 and the 8088 and all of that kind of stuff, when you just had the A register, which was a single 8-bit. And then as things have been sort of tacked on, you're sort of seeing, we're sort of mining the strata of going back through, you know, 50 years of software, of hardware engineering. The only sort of weird, noteworthy thing is that if you write to AX or AH or AL, you're literally like just plopping in those bits and leaving the white bits unaffected. But special cases, you know, we're C++ programs, we're used to special cases, right? So this shouldn't be too hard. Is that if you write to EAX, magically, it's as if you set the top bits to 0. It's useful, it's useful. It's actually a pain that these things don't actually clear the other bits, but they're used by too many old programs for us to actually change the meaning. So when AMD decided to make it a 64-bit architecture, they said, like, hey, this is where the madness ends. Okay. So those are registers, we've seen operands. That's pretty much all you need to know. So you all know assembly now, well done. The thing is, if you're looking at assembly, it's usually because you care about performance. Maybe you just, I mean, hopefully you'll look at it just because of the sheer joy of reading assembly after this talk. But right now, most of you who have looked at assembly before are worried about the performance, and I have to insert this disclaimer here, which is that reading assembly is not going to help you understand how fast your code is most of the time. So the number of lines of code may correspond to the number of instructions. Each instruction may take longer or not, depending on the type of instruction. Some of them take a third of a cycle nowadays on these modern machines. Some of them take 0 cycles, which is amazing. Some of them take hundreds of cycles. So you can't just read the output and go, this is fewer lines than the previous thing. This must be better. You have to know a little bit. So always, always, always benchmark. There are lots of good libraries for doing benchmarking. Google Benchmark and these other two. I haven't tried the other two. Google Benchmark is what I use. And obviously there's QuickBench. Hi, Fred. QuickBench, which is an online version, so much similar to the Compiler Explorer. You can type in your code and get a sort of benchmark of how the things stack up against each other. So with that said, though, you can develop an intuition. You know, it's definitely the case that if you compare 3,000 lines of spaghetti-looking assembly code with mov EAX, 12 return, the mov EAX is going to be faster than the other one. So knowing which things are going on is important. And things like how many times do constructors get called? Does new and delete get elided? Who was here for Jason's talk? Yeah, it's surprising how many times the compiler basically completely ignores everything you said and go, I know what you're doing. Okay, so with that, all those caveats, I want to show you some examples of how awesome your compiler is. So the first thing your compiler is awesome at is maths. And I get to say maths with an S on the end here, and nobody takes the mickey out of me. All right, so now we cue the live demo part where everything could go horrifically wrong. So we're going to start off with this extremely simple test case here. We're just going to have x and y, and we're going to return x minus y. And I'm going to bring this up. And phew, Having just rebooted my computer, it's a bit surprising that that actually worked. So what we've got here is a function which takes x and y and returns x minus y. So we know that the parameters must have been passed in the RDI and RSI registers, because that's what the ABI says. Although because we're using 32-bit, our ints are 32-bit, we only need to look at the E part of it. So EDI and ESI here are the two parameters that came in. And then we need to get the result of the subtraction into EAX. Now, on a normal rational computer system, like an ARM, you would probably just have a sub which says, put the result of the subtraction in R0, and the two inputs are in the two input registers, which I actually can't remember off the top of my head. So, the instruction could encode the whole thing in one go, which would be great. But again, because we've got this sort of destructive minus equal primitive that we have to build everything out of, the first thing we have to do is we have to copy one of the input operands into the result register. So that's what that line 2 is doing. It's saying mov EAX, EDI. It says, hey, copy X into the result register. And then we do result register minus equals Y. And then we're done. So pretty straightforward. We didn't have to preserve any registers or anything like that. We didn't use any of the registers that have to be preserved. And frankly, you don't really need to worry about that. The compiler will definitely reserve and unreserve the registers for you. So you can just normally ignore all the pushing and popping. So that's cool. What if we were to change this to a plus? What do you think it'll change to? Any takers in the audience? Add, yeah! So we'll see it turn into an no. All right, so I didn't really set you up for success in this because I glossed over what the LEA instruction was. So you can subtract using the sub instruction, you can add using the add instruction. What the LEA instruction is the address of kind of instruction. So we had that really complicated way we can refer to memory as like some pointer plus some other pointer and an offset and some 1 times 2 or times 4 or times 8. Well, the LEA instruction says, that's great. Can you do all that calculation as if you were going to read from the address RDI plus RSI, but don't read from it, just tell me the address of that, which is just basically an add instruction in plain clothes with the nice side effect of the fact that we get 2 operands on the right-hand side, and the destination is different from them. So we get to say, add RDI to RSI and put it into EAX. Now, of course, those aren't pointers. They're just 2 integers. But as long as we don't dereference them, that's completely fine. So we're good. Now, the other thing you notice the LEA instruction could do is I can multiply one of those by 8, and it's still one instruction. How cool is that? So the compiler is smart enough to notice what I'm doing and pick an instruction which does exactly what I want it to do, even though I would have never have thought of that in a million years. So why don't we just change this to take 1 parameter, and then we just start experimenting with what we can do with multiply. So I'm going to say x times 1. Obviously, it's not going to do a multiply. Oh, incidentally, we're on GCC 8.2 here, and I've got it on -02. And I'm targeting the Haswell architecture, which is sort of a middlingly good server quality CPU. It's important to check that, by the way. Always put march if you can. So anyway, times 1, it just says a mov. Times 2, it's going to use an LEA, and it's actually going to add it with itself, interestingly, rather than if I then do with 4, now we have to sort of take the address of 0 plus RDI times 4. Cool. So it's building all these things out. So 8, we know that it's going to be problematic as soon as I pick anything that isn't 1, 2, 4, or 8, because those are the magic numbers that the LEA instruction gives us. So let's try 7. Still no add, or multiply instruction even, right? We're doing multiply by 8 and then take away one of the things you first had. And of course, the compiler is smart enough to do all of these other things. So times 3 is RDI plus RDI times 2. And, this is great because, we're told never to like prematurely optimize our code, and we shouldn't do. But thankfully, the compiler authors have already sort of sat down with a big book of optimization. And every time we run our compile, they're doing every kind of compilation and optimization for us. It's brilliant. But, it gets more complicated. If I put 16 here, it's now using a shift. This SAL is a shift. And you've probably seen people who write code still where they're kind of like, I'm clever, I'm going to use the shift operator. I'm going to do, instead of multiplying by 16, I'm going to do left shift with 4. And you're like, so that's a clever person who knows that they can outwit the compiler. But then the compiler's pretty smart. But, if it gets too complicated, it has to use a multiply. It's gotten too complicated. Presumably the compilers have just bailed and said, had enough. Or just use a multiplier now. And as we all know, multipliers are slow. So luckily, I am smarter than the compiler, because I can build a multiply by 65599 by shifts and adds, right? And shifts, so I multiply by 65536, multiply by 64, take away A, it's all add, I've sat down, I carefully worked it out, and I'm going to compile it, and you can see how much better that I am than the compiler. You ready? That's right. The compiler is smarter than me. It knows my game, and it knows that I'm wrong, and it's going to save me from myself. So the compiler has derived that that is a multiply by 65599, and it is writing it in anyway, because it turns out that this trick, multiplies are slower, but not since the 486 have they been that slower than the shifts and adds that this would require. So for example, if I now change the architecture to I486M32, it will happily generate that code for me. So, it knows how fast the CPU is. But of course, if I were to actually write this code, A, it shouldn't get through code review. And you should thank the person who didn't let it go through code review. I could write it this way. And actually, the compiler has got a smarter trick than the one that I did by hand. So, I can't win. And of course, this is brilliant because it's intention revealing. I'm multiplying by, admittedly, a nasty constant, but let's forget that for now. And if I'm targeting a 486, it will do the right thing. And if I go back to a Haswell over here, if I can remember, if I go back to a Haswell, it'll go back to using the multiply by 65599. So the message there really is trust the compiler to do the right thing. Don't try to be too clever. The compiler has similar tricks for division and modulus, particularly if they're with compile time constants. There are some really, really clever tricks it does, and I encourage you to look at one of my other talks, I go into the division thing in quite some depth, but it's cool, it's fun. Clang even is smart enough to notice when you're doing like a sum between two values, like between 0 and n, if you're passing into a parameter, and it will replace a loop of adds that you've written with the closed form solution n plus 1 over 2, which is just mind-bogglingly clever. So the compiler is really, really good at maths, and you should trust it. Write the code that you would like to read, and trust the compiler to do the right thing. So that's maths. Compilers are also awesome at vectorization. How am I doing for time? Oh, good. What do I mean by vectorization? So, I forgot to tell you about that. Sorry, on the register page, I blasted through all the registers, and I didn't say anything about those XMM and YMM and ZMM registers that were at the bottom. I left that there as kind of like a tease, and I should have told you. So, the XMM registers are used for floating point operations nowadays, and they're also wider than the 64-bit general purpose registers. So the XMM registers are 128-bit, the YMM are 256-bit, and the ZMM are 512, although I think there are 1,024 variances now, which is just mind-bogglingly wide, right? These are huge registers, and they're not to store numbers that are that big. They're treatable as blocks of smaller sized elements. So for example, an XMM register being 128 bits wide, you can fit 4 32-bit values in it. And then the multipliers and things act on each of those individual 32-bit blocks together. And this is vectorization. This is taking something which can be parallelized at the instruction level as you're writing it. You're saying, I can do these 4 at a time. Brilliant. But that sounds complicated, right? These are esoteric registers. These are esoteric instructions even. And so writing this kind of stuff is usually something you hand off to like LinPack or some of these linear algebra libraries that then some smart people have written, maybe handcrafted assemblies to take advantage of these. I'm going to show you that you don't always need to go to those lengths. So here is a silly function which is totally non-idiomatic, using raw loops and all the things, and using single letter variable names, which we should stop using. But we have a vector called v, and we are going to go over each element in that vector, and we're going to sum up the squares of all of the things that are in the vector. So every element I in there, which is an integer, we're going to square it and we'll add it to a result, and we're going to return that result. Maybe we're going to do like a root mean squared type thing or some other statistical thingamajig. So I'm going to look at this over here. Now, I was hoping here, of course, that the compiler would be super, super cool and it would use some vectorization, but it hasn't, unfortunately. And that's because I haven't yet turned the optimizer up to full pelt. And for GCC at least, vectorization needs to be on 03, although you can turn it on independently. But this is kind of a nice, succinct example I can show you and walk through what an algorithm looks like when it isn't vectorized. And then when we see the vectorized version, maybe it'll help you put those two things together. So these first 2 lines of the output here, lines 2 and lines 3, they're reading through RDI. Now, RDI is the first parameter, and the first parameter is a reference to a vector. to the CPU, references and pointers are exactly the same thing. There's no distinction at all. So effectively, RDI points to where the vector lives. The vector itself, obviously, isn't the data. It's not the integers. It's a data structure in its own right, which we know has pointers off somewhere else that has the actual array of integers. And it just so happens that the first and the second pointer in that block that it's pointing at point to the begin and the end. So what those first two lines are doing is they're moving begin and end of the vector into RCX and RSI. And you can't really see the coloration here, but the coloration actually comes up pretty well here. So the light blue in the background of the ZOR EAX, which is the next line, corresponds to the int res equals 0 line on the left-hand side. So ZOR EAX, why on earth would you exclusive OR a number with itself? Well, in fact, a register with itself. I mean, what is X exclusive OR with X? 0. So this just seems like a very silly way to set EAX to 0. But there are two reasons why the compiler hasn't just done the far more straightforward mov EAX, 0. One is that ZOR EAX, to encode the instruction, these bytes are being placed in memory that the CPU interprets as these instructions. This is the machine code that this assembly becomes for ZOR EAX is 2 bytes long. Whereas if it was mov EAX, 00000000, it would be 5 bytes long. So the constant itself would take 4 bytes of storage in the program. The other thing is that the CPU is smart enough to know that people have been using this trick for years and years and years, and it will look ahead and it will spot these, and it will actually pull them out of the instruction stream. So in the front end of the CPU, it just says, oh, at this point in the program flow, we need a new bucket, which I'm going to call EAX for now, but it's just got 0 in it. And that's essentially free. So the front end, there's a whole, I'd love to talk to you about how the out-of-order execution systems work on these modern CPUs, but it's just magic. It's magic and it effectively takes no cycles, which is just wonderful. So the next thing we do is we say, is begin equal to end? And if it is, go to L4. So if begin is equal to end, obviously the structure was empty, and we just return. And we return with the EX register being 0, so result was 0. So that was there was nothing to do case. And then we fall into this L3 loop here. And it's pretty straightforward. We're reading a value from the begin pointer. We're moving the begin pointer forward by 4 to account for the 4 bytes we've just read. We're squaring that with an imul. So this is x times equals x, or sorry, I times equals I. And then we're adding it into the accumulating register, the EX, the result register. We say, have we now incremented begin to match end? If not, we have more work to do. Keep going. So that's pretty straightforward. I think it pretty much reads the way that you wrote it. Now we get the cool stuff, because I'm going to turn on O3. You ready? Lots more code. But it's not actually that much more scary. The first few lines are basically the same. There's some comparisons and reading of whether begin is equal to end. There's this big block here, which is essentially getting the size of the number of elements that it needs to process. And it's comparing it with 24. If there's more than 24 bytes worth, then it knows that there's not any value in vectorizing. And it's just going to go off to L8 there, which is at the end of the routine. And it's just a copy of effectively the same code that we just saw. It's just like doing them one at a time. But once we have more than 24 bytes worth, it's worth reading them out 32 bytes at a time and processing them in parallel, which is what the rest of this is going to do. I'm going to gloss over there, but this is the main part. This loop here, this L4 loop. Now we're into the cool stuff, because we've got vmovdq, YMM2, YMM word pointer racks. This is reading into the YMM registers, which are the 256, 512 byte wide, i.e. 512-bit, 32 byte wide registers. So in one instruction, I've picked up 32 bytes worth of integers. I then move on by 32 bytes, because that's how much I've done. I can then square them all independently, so that VP mul D takes the same time as a normal multiply, but it's taking each of the 8 integers I've picked up and squared them independently, and then I'm accumulating them into YMM1, which isn't quite what I wrote, because each of those 8 that I picked up is now being accumulated into 8 separate slots of an accumulator register, which means I'm currently getting 8 independent results. So then I keep comparing and I go round. So the result of this is I've been able to chew through in very few instructions and pick up blocks of these 8 at a time, square them, add them to each other, and now I'm left with these kind of 8 subtotals. But the cool thing about that is that I can add those subtotals together, and now I've got the full total. And that's what this horrible extract VP add verscroll nonsense is doing out in here. And then at the bottom, it falls into the loop that just does the remaining few. So if there's not an exact number of 8 of them, multiple of 8 of them, there's a little tidy up at the end. So that's pretty cool, right? I didn't have to know anything about this, but the compiler has done all this work for me. So yeah, effectively, it's been able to rewrite my code internally into these 8 separate subtotal registers, and then it's going through them 8 at a time. And then this middle block here, the force-id, that's a single set of instructions. I can do that in parallel. And that's, when I say in parallel here, obviously there are multiple ways things can be in parallel. There can be multiple threads. There can be multiple units that are running different parts of the code out of order with respect to each other. This is very explicitly parallel at the instruction level. I'm actually saying, can you do 8 of these at once? And that's so cool because it's not that much more expensive than doing them one at a time. We're just going 8 times faster. Of course, we'll run out of the memory bandwidth pretty quickly as we start chewing through memory so fast, but that's a different problem. Now, of course, I said it was unidiomatic. You know, it was a raw loop, and it was written to just work with ints. Now, we should all be writing code that looks a little bit more like this now, where we're using standard algorithms. And, I mean, heck, there was no reason why I chose int. I could have used any type. It would have worked with any sort of type, as long as it supports squaring and adding. So I'm going to rephrase this in terms of standard accumulate. I'm going to use type name t, colon, value type in parentheses, sort of get like a default value to start with of a zero-ish version, which works for this. And then I'm going to return x plus y times y in my little lambda, which is how I accumulate. So when I have my running total x and I'm taking my new value y in, I square the y value and add it into my running total. And of course, the compiler will not be able to see past all of the layers and layers and layers of indirection. Oh, in fact, it hasn't generated anything at all. Because, as Walter will know, this is not a function. This is a function template. And so I have to turn it into a function. So what I typically do with this is I'm going to write a little test function here. I tried explicitly instantiating it. It didn't actually work earlier. I thought I was going to try that. So we're going to do const vector of int and v return some square. This is scintillating to watch, I know. Woohoo! And now we get, basically the exact same code as we did when I hand rolled it. So there's no cost. We should be writing code like this on the left-hand side. If it fits in what you're doing, use the standard library, use the standard accumulate, and don't be afraid of it, because the compiler sees through it all, and it will generate the same optimal code. And now, of course, we can play with it a little bit more. You know, this is what Compiler Explorer is all about, is I can go in here and say, well, what would happen if these were long? And the code is changed a bit here. It has to do a bit more work because it turns out there is no multiply that works on longs inside, that are packed inside an XMM or YMM register. It has to build the multiply out of two parts. So it's a bit more work, but ultimately it's still doing them 32 bytes worth at a time with a bit more overhead. What if I were to make that a char? Well, it gives up. You can see we're back to that form that we saw before where it's doing them one at a time, which is a shame. So there's no parallelizable thing where we can take a vector worth of chars and multiply them themselves, at least on this architecture. Now, of course, if you're doing this kind of stuff, you're probably not using integers because integers tend to have nasty properties. You usually have a bunch of floats. So we're going to use float here, and we're going to see, that the same thing's going to happen here. Although I'm sure Simon Brand is grinning to himself in the front. So, it's broadly the same. There is, we're checking to see if it's big enough. We're doing some work. We're zeroing our accumulator. We start strong. We were going to read 32 bytes worth of floating point values. We're going to move forward by 32 bytes. We're going to square it in place. And then we're this is sad. Oh, terrible. There's a page of code before we loop back round again and do the next thing. And again, right, measuring by the number of lines of code is not something you should typically do, but this is unfortunate. And we're like, why does it need to do all of this work? And the answer really is, unfortunately, floating point numbers are not commutative or associative. So that means that you can't add them in any arbitrary order you like. For integers, x plus y plus z is the same as y plus z plus x is the same as z plus y plus x. So the compiler was freely able to separate them into 8 separate subtotals and add them all up separately and then top them all up at the end as a supertotal and get the same answer as if I'd gone through them individually one at a time. With floating point numbers, because the relative precision of the two numbers you're adding together affects the relative precision of their output, which then obviously has a knock-on effect, amongst many other things to do with signaling, not numbers and exceptions and things and errors. You know, the compiler is not at liberty to reorder these operations, and so it's forced to do them serially. And so it has to, the best it can do is read a whole bunch of them, square them in place, and then kind of shuffle them down and add them to get one total each time, which is what all of this code is doing here. And that's sort of sad. Now, there is potential good news coming. We've got standard reduce coming, which will allow us to say that we can use a parallel unsequenced algorithm on this, which would allow us some leeway to tell the compiler, it's okay, the sequence is not important. Now, obviously, it may be, if you care about the precision, for example, of the result of this, then maybe you do have to do them strictly in order. But if you're just getting some kind of rough approximation, then maybe it's okay to allow it to be unsequenced, in which case the compiler might have latitude to do this. But unfortunately, there is no just unsequenced, so you get the parallel part as well, and maybe you don't want to have the overhead of that. There is also another nuclear option, which comes under the extremely fun, literally, fun, safe math optimizations. I'm pretty sure that's how you pronounce it. Oh, what have I? Oh, I can't spell. Excuse me. Oh, no. Now I can't even see where I'm clicking. So when I say F-unsafe math optimizations, I'm telling you a whole grab bag of things that I'm saying, actually, it's fine. And at this point, you have to assume the worst. I think Chandler Carruth calls it unbounded mathematical imprecision or something like that. And so you're basically opening yourself up to anything here. But just to get a glimmer, just a taste of how lovely it would be if you were able to do this normally, we've turned them all off, and now the compiler can reorder everything it likes. And if we go down to our little loop here, it's better even than the integer version. Look, it's only that many instructions, that core part. We're reading them, we're squaring them, and adding them in one go. This extraordinarily long and complicated sounding instruction, which I'm not even going to pretend to pronounce, this VFM add thing, this is a multiply add. This is the way that floating point works once you've unpacked the numbers, is that to do an extra add while you're already doing a multiply is cheap as chips, so you can actually sort of fold it in. And in fact, most floating point units are just built out of multiply adders. So we can tap into that here. This is squaring YMM2 and adding it into YMM0 in one instruction. And it takes just as long as a normal multiply or add. And then we go around. And then there's the bit at the end here. This is all this sort of like sideways adding to get the final total. So if you don't mind unbounded mathematical precision errors, and who doesn't, you can use this. There are various pragmas you can use to turn it on and off as well, maybe in sort of targeted areas of your code. But I'll be honest with you, I was trying this last night, and I couldn't get the pragmas to work the way I wanted them to. So caveat emptor. All right. What else are compilers awesome at? Control flow. Now, this is a small and strange thing to pick on, but in the world of lambdas, code like this can start to appear. That's not actually, oh, it's a bit small. And that is where we've got like a routine, and we've got this inner loop that's looping over a bunch of things, and then if the parameter that was passed in is A is true, we're adding to the total A, else we're adding to the total B. Now, obviously, this is a daft thing for anyone to actually have written, but it's slide code, so give me some latitude. And again, I've seen things like this where I've passed an immediately invoked lambda into something else that's like iterating over a bunch of things. And rather than me create two different lambdas, one that adds to total A and one that adds to total B, and like conditionally pass in one or the other lambda, I pass in a lambda that does this inside. But it's daft because is_a can't change during the body of the loop. And so we'll be forever comparing is_a and then doing two different things. You know, the loop iteration will be dominated by us just comparing this is_a every time. But luckily the compiler has our back here. And so it's clever enough to hoist that is_a check outside of the loop and turn it essentially into the code which is, if is_a for auto val in array, total A plus equals val, else for auto val in array, total B plus equals val. And so we do the comparison once, and then because we've unlocked this middle part where there's no comparisons going on, the vectorizer has leapt into action and has decided to vectorize the whole thing. So we've just got this one test at the top followed by this beautiful set of vector instructions. And in this particular example, it's known ahead of time that there's exactly 32 integers, so it just blasts through them and unrolls the whole thing. So that's awesome. The compiler has us on this too. What else are they awesome at? And I'm sure there are much better examples of control flow analysis and constant evaluation and code hoisting and things. But the thing that's closest to my heart are architectural tricks. what do I mean by that? I mean, the LEA thing we saw earlier is a kind of an example of an architectural trick where like a specific instruction has been kind of dusted off and used for something that was never really intended for. How many times have you had an integer and gone, I wonder how many 1 bits there are in this integer? Anybody? Oh gosh, actually that's a lot more than I was expecting. Wow. Normally I have to come up with a justification for why it's useful to do this, but I'm not going to today because there are enough people who are. So anyway, this is how I would count the number of set bits in an integer. I'd say, I take my integer a, I start my count at 0, and I go, while a isn't equal to 0, while there are still bits that are set in a, I'm going to increment the count because there's at least 1 more bit set, and then I'm going to use this super neat trick that I got off the internet on bit twiddling hacks or, what's the book? Yeah, Hacker's Delight, yes. Which is the clear the bottom set bit. So a and equals a minus 1 clears the bottom set bit of a number. And actually, joking aside, it's quite fun to write out like a 5-digit binary number and work out why that's true. It's just fun. Do it, trust me. Anyway, no one's going to go with that, are they? So anyway, we clear the bottom bit and then we go around. And so how many times can we clear the bottom bit, the bottom set bit, I should say, before we run out of bits? And then we return the count. Let's see what... And those that saw my other talk, no spoilers, please. So this is GCC. GCC has done an awesome job of basically replicating my loop. You can kind of, again, squint your eyes and see the same kind of flow over here. And it's been able to notice that the a and equals a minus 1 is so common that there's actually an instruction that does that. That's so cool. Except Clang says, hold my beer. And in fairness, GCC trunk also now says that too, but this was... Clang says, there's an instruction for that. It's so common that we can just do this whole thing. Just think about what's happening here. We've taken an algorithm on the left-hand side, which is linear in the number of set bits, and we've turned it into a constant time operation on the right-hand side. That's so cool. That's so cool. Except that if we do go to GCC trunk, we see something else. We set the result to be 0, and then we set the result to be the pop count. And you think, oh, GCC, you've done something daft there. You see, look, you've done this extraneous instruction here because pop count completely overwrites EAX, right, with the result of how many bits were set. And then you pore over the Intel manuals and you'll find in the errata section, you'll notice that the population count instruction has an artificial dependency on the previous results of EAX. That is, in the dependency tracking system of the CPU itself, which it uses to schedule things, it doesn't notice that pop count EAX actually completely obliterates whatever EAX was before, so you can discard the result of anything else beforehand. And that means that if you just were dividing and putting the result of the divider in EAX just before that pop count, the pop count has to wait for the divide to finish. So XOR EAX, this is its other hat, as well as being small and in terms of the binary output. Again, this is a way of telling the CPU, EAX no longer depends on any previous value of EAX. So that breaks the dependency, and it works around a CPU bug. And also, I mean, how many times have you folks seen rep-ret in the results, the output here? Yeah, it's a blight, because it was a bug in AMD CPUs. If you jumped to a return instruction, there was a misprediction because the system that tries to predict where branches are going hasn't had time to catch up with what's happened, and it gets completely out of kilter, and eventually it mispredicts, it has to come back and do all the work again. And so by putting a single rep prefix, which is normally used for like repeated instructions, there are some like a memcopy-like instruction where you repeatedly do this thing. It has no effect on a ret, but it's just enough to wiggle out of the bug on the AMDs. And unfortunately, every compiler now has implemented it as a fix, and so you'll see it all over the shop. That's another reason why if you say march equals Haswell or something like that, you're saying like, it's not an AMD, it's fine, you can ignore, drop that. Oh golly, I'm running out of time. Another thing you might do, if you work with computers that use the wrong endian, different endian, I shouldn't be endianist. There are reasons to have both endians, but you find yourself writing code like this. Obviously, you realistically use htonnl and htons and things like that if you're using networking code. But if you are reading data and you definitely know that your architecture is different to the architecture you're reading from, you're going to need to take 32 bits values and sort of switch it around and put it back down again. Luckily, Intel know that we do this a lot, and so there's an instruction for that as well. And it's even smart enough. There's actually a version of move that doesn't turn up where you're moving from memory, where it moves and switches in one. And if I had time, I would show you that calling switch bits on a value that's being read from memory will just use that move that moves and switches in one go. So the compilers are pretty smart. They know how to take advantage of all of the cool features that your CPU has. This is my favorite of the whole talk for a couple of reasons. So how many times have you found yourself writing ispus or something like it? Obviously, hopefully you'd use std_ispus. There's a few hands that have gone up here, right? And, you know, it seems straightforward. And if I would ask before I actually went into all of this, if I were asked how many compares there were going to be in the assembly instruction, I said, well, there's 4, maybe 5. I don't know. That seems to be it. You know, you have to compare against each of the characters, right? There's no getting around it. I need it to, if any of those are if the character is any of those ASCII codes, then I need to return true, else it's false. Well, smart compiler engineers know better than me, which is not really hard. We have one comparison here. This is super cool, right? If I mouse over this crazy-looking constant, you can see that what it is basically all zeros with a couple of 1 bits in it. And what it's effectively done is it's built a table of Boolean values. And it said, okay, well, you know, like naively, I might write a big 256 element array of Boolean values, and then I would populate true in only the space, the arc, \r, \n, and \t of that array. And then I'd look it up in the array, and I'd be like, hooray, branch-free programming. But the compiler is smarter, as always. The first thing it says is if it's 32, or if it's above 32, that's it comparing DIL. So the IL is the bottom byte part of the RDX register. If it's above 32, 32 is space, and all those other control codes are less than space, then it can't possibly be a space. Obviously, it doesn't know that it's a space, but it can't possibly be true. So it jumps out to the ret. Otherwise, it takes that constant and it shifts it down by the actual ASCII codes that it's got. And so, and then, sorry, ands out the bottom bit. So we're basically selecting the ith bit. So it's as if it's taken my 256 byte array. It's then gone, well, there's the top 33 and above are all false, so I'll just compare that and throw it away. And then using a whole byte for each of these balls is silly. Let's bit pack it into a 33-bit value and use that. And that's what it's done. That's so cool. What's unfortunate, I will come back to this, but yeah, if that helps you visualize it a little bit more, there are just 1 bits where the character codes for things that are considered to be spaces are. We take this, we shift it down the number of times that the character is. So if it was 32 for a space, for example, we would shift it down 32 times, and that 1 bit there would end up at the bottom, and we'd be returning true. Cool. Now, the fun thing about this, I'm going to go back. Oh, whoops. If only I knew how to control slides. I think we all saw in Hannah's talk that I'm not very good at that. What if I were to switch the C, this line, and this line? This is how it used to look. Oh, that's sad. So unfortunately, we're starting to move towards the part of the talk where it's the compilers are amazing, but. And so this is one of the first sort of buts of the talk. And unfortunately, GCC, in the way it builds the parse tree, and I don't understand fully, I filed a bug and they're looking into it. It doesn't, this cool trick doesn't happen when we get the N and the R the other way around. And I don't know what triggers it, but I'm glad that I saw the good case before I saw this case. Otherwise, we would never have actually seen this example here. So it's worth checking the output of the compiler, although even though it gets it right most of the time. And for those wondering, Clang, wherever Clang is, there, Clang uses the right trick, a slightly different variant of the same trick, and doesn't suffer from the reordering problem. So +1 to Clang there. Okay, where do we got down here? We saw that. All right, yeah, so as I hinted, we're now moving into the slightly less awesome stage, which is still pretty awesome, so don't worry. Compilers are cool, but my clicker is not. Oh, there it is. So basically, they all boil down to this. Compilers do everything they can, and sometimes you might think they're clairvoyant and can see what you're actually trying to do. I mean, like, think about that multiply example, right? It really went, I got you here. But this section is mainly going to show you things like this, where I've rewritten, this is now summing the square of y x times. And, you know, we know it's the square of y x times because that's what I called the function. The compiler has no idea that that's what the square function does. So if we compile this, then we get an unfortunate mess of calls and adds and stuff. And it has to call the square function at least X times because it has no idea that the square function doesn't do some crazy thing like printf or something. Now, as soon as it can see inside that body of square, if I were to implement square up here, return X times X, then, oh, num times num. See, I used num here, slightly better. Then we get back to, well, no, we get to a case now where it can actually know that it can square the thing and then multiply it by x, and then the answer's right, so it doesn't even have to loop. But if it knows that the function is pure, that is, the function does not do anything other than return a value which is a function of its inputs. Now, this is slightly off-piece for standard people. We can say GNU colon pure as a decorator at the front. Oh, 2 colons, thank you. It still doesn't know what square does, but we've promised it, Scout's honor, that we're not going to do anything that's impure, which probably is sensible anyway. And so we're going to call square once and multiply it. So we get some benefit of that. Now, I'm not at all proposing that you go off and use underscore attribute pure or GNU pure, things like this, but be aware that if the compiler can prove that a function is pure, that could be a useful thing for you to have. It's also worth noting that as we start using link time optimization, actually, who uses link time optimization? Okay, that's a healthy number of people, even people up in the galley. So that's good news, because the link time optimizer, even if it can't inline that function, one of the things it can do is it can note the purity or otherwise of the function and put that into like the general program database. And so when it comes to link and generate that call to square, it may notice that it's pure and can get away with a bit more, or a bit less, a bit fewer, one of those words, work. So that's cool. What have I got going? I'm running out of time here. Everyone likes to hate on virtual functions, so I'm going to quickly talk about virtual functions, although this is, in the interest of speed, I'm going to get there. So this is me just making a func object which returns the x squared. I know I'm very unimaginative when it comes to like examples. And at the moment, we get the happy case here. Here's our L4 loop with all of the cool vector instructions again. But as soon as I put the virtual keyword up here, like I would do if really I was going to have a switchable, pluggable function here, then it's just going to completely go to pot, right? There's going to be virtual function calls every single time, no inlining. It's just going to be a complete train wreck. Except actually, it's not great, but it's not as bad as you might think. So this L5 block here, now it's doing one at a time, unfortunately, but there is no call instruction in that block. Now, you're thinking, but there's a virtual method that I'm calling there. The compiler absolutely has to know that it's got to go off and do something that is runtime dependent. But GCC has something called speculative devirtualization. Yeah. And so what you'll see it's doing is in this line 20 and 21 here, it's reading out the value, and it's reading out the value of the function that it would jump to. It said, okay, well, if I have to jump to this function, this is the address of that function I'm going to go to. And then it makes a bet on line 22, and it says, I've only ever seen one implementation of this function. I'm skeptical that other implementations exist. What if I were to just compare where I'm about to jump to with, and if I could scroll off there, with the actual function, the one and only implementation that I know of? It says, if it's not equal to that, go to L6. L6 is like, okay, I'll go and do all the hard work. Otherwise, it is the one I know about, in which case I'm going to inline it here. And I'm going to imol ESI. So this is an inline virtual function call. How cool is that? And then we add to the next one and we go around. And so that is really exciting. And Clang is getting there with this as well. There's a whole bunch of work that's being done by Piotr Padlewski and other people that's making that come to Clang as well. But there's still opportunities for excellence here, so for our compiler writers, because you and I can see that calling operator paren can't possibly change the nature of func, right? So every time I'm going to call that function, at the moment it's reloading the vtable pointer every time. So, the function pointer on line 20, it's reloading that function pointer every time. It's the same value, right? Now, there are some crazy ways in C++ that you can actually change the dynamic type of an object. Never do them, please. But because we can see into it, we know it's not happening. So what could happen here is that it could derive that value doesn't change. It could hoist it out of the loop, so it doesn't need to reread it every time. And then it's like, well, I'm comparing with a constant in here, and there are two possibilities. Either it's always equal or it's always not equal. If it's always not equal, I go off to the other sad part where it's a different different group entirely, different block entirely where I am going to call the virtual function. Otherwise, I'm left with the imol add and go back around to the top of the loop again. And then you're like, well, hang on a second. If you're smart enough to have done that, the vectorizer can turn back on again and we can get vectorized stuff. So I think that this could be as efficient as the original version with just a single comparison at the top. Now, whether the compilers will ever get to that level, I don't know, but I have a special place in my heart for virtual functions, that's all. Okay. All right, another moment of slight sadness here. So even though there was some sadness in that previous one, there was a golden light at the end of the tunnel. So this one had me befuddled for a while. So this is just an accumulator, right? It's a class that has a total, and we give it vectors of ints, and we keep adding them to the running total. Maybe at the end, we'll get the sum total out. And again, this should be. I mean, I'm on 03. All the good flags are set, but it didn't vectorize my wonderful loop here. And I was flummoxed, but what's happening here, I'll put it out to the audience, but we're running out of time. What's happening here is that the compiler is unable to prove to itself that m total, which is an integer, does not overlap with any of the values in that array. Now, you and I think, can look at it and say, I don't think there's any way that we could somehow embed an adder object in the middle of a const vector int array without it being undefined behavior. And I would love for someone to tell me how that could be true. But I'm no expert. But we can do something here, because what C++ undefined behavior rules say is that it would be undefined behavior for it to alias a different type. This is the whole thing about reinterpret cast. You can't really reinterpret cast because the compiler is allowed to do things like this, where if I turn that into a long instead of an int, it now knows that the integer array can't overlap with the long. And that would really be undefined behavior if we somehow managed to get that to be the case. And now we're back to our good sort of nice, fast-ish. I mean, it's a long, so it's slightly different block there. There is another way to solve this, and this is where you can start throwing rotten eggs at me. Partly because I'm running out of time, but partly because who knew you could put restrict as a member function, like thingamajig, whatever that spot is called. So I can also say __ restrict, which is a verboten magic keyword from C, which says, I promise you that nothing overlaps, none of the pointers that in the thing that I'm putting restrict on, in this case, which is the this pointer, I'm promising you that it doesn't overlap with anything else, although the jury is out about what it really, really means, and I'm certainly not capable of explaining what goes on behind the doors of people who decide such things. But anyway, I noticed that this also saved us here. So just be aware, aliasing is a thing, and the compiler can't, unfortunately, always prove to itself that aliasing isn't happening. Another thing the compiler can't do for you is if you tell it that your struct looks like this, it can't do anything other than lay your struct out exactly as you asked it, even though inside it's wincing at the 7 bytes that you're missing between A and B there, and the 4 bytes between C and D. There are tools that can let you find these things. There's something called PA hole, which is an actual drop-down tool on Compiler Explorer that will sort of say, hey, you've got a whole big hole in your object here. It's worth looking at, but you asked it to do this, and unfortunately it has to do it for ABI compatibility reasons. Another thing that it definitely can't do is it can't. Does anyone recognize this sort algorithm, just quickly? I think it's BOGO sort. Yeah. I actually wrote tests for this and everything. I'm so sad. And it's actually quite fun because you're sitting down and trying to like measure the running time of it, because essentially it's O infinity, because there's no guarantee it will ever actually complete. But yeah, we're just shuffling. So yes, if you don't use the right sorting algorithm, and I would contend that BOGO sort is never the correct, except in, actually it's the perfect one to get that, elicit that response on this particular stage. This is the one and only time it'll be useful. Okay, so it can't obviously rewrite your algorithms, although we did see it do a couple of times where it turned my loop into a pop count, and it'll turn a sum of things into a closed form solution. Those are extremely rare and extremely special case. So, in conclusion then, yes, sneeze. In conclusion, compilers are cleverer than we are, unless you happen to be a compiler writer, in which case, thank you very, very much for what you're doing, because you're doing such a great job. And I think they're much maligned. And a lot of this stuff, obviously, a lot of the exciting stuff happens on the front end of the compiler, all the new things that come into the standard. But there's so much work as new processes come out, and as new ideas get mooted, and as people discover new clever tricks for the architectures that they work on, and they codify it in the compiler, and then we all reap the benefit every time we hit make or build, whatever you're. And hopefully you realize that now that assembly isn't that scary, maybe? Again, remember, Shakespearean poetry. So trust your compiler and don't compromise readability. Those are the serious points, actually, is like, it's so tempting to see those things that you've seen like a 20-year-old code base where compilers weren't necessarily sophisticated and kind of perpetuate the crazy shifting around and shifting down instead of just using multiplies and divides and trusting the compiler to do the right thing. You know, write what you would like to read, not what you think the compiler might need, because the compiler, as it turns out, has been working on this a long time. Be aware of these limitations in the compilers: aliasing, visibility, structure layout, and algorithms. So aliasing, you can use the type system to your advantage. There was a small type talk sometime earlier today, or yesterday, that is another way of like saying, well, we can keep things in separate domains. They may still be integers, but if this is a quantity and this is a price, then never the twain shall meet. We know they can't alias with each other as well, which is another benefit. Pass by value is something we can do quite a lot now, and if you pass by value, you know that it can't alias with anything. That's kind of cool. I've noticed also that if you do avoid raw loops and you tend to use like little lambda functions and things that are inside standard algorithms, it becomes a lot less convenient to access state that lives outside of the immediate scope of the lambda. So that typically means that, again, aliasing is not a problem. So for example, going back to that mtotal version that I was doing, you could capture the this pointer inside of it, but it might be much nicer just to use an accumulate and add them all up and then just do mtotal plus equals the result of std accumulate of that nonsense. And then it wouldn't have aliased and there'd be one add at the end and we'd be happy. And then I think I should really take that off. Ignore that last advice there. Don't use it, underscore restrict. For visibility, unknown calls limit, inhibit some kinds of optimizations. You can use GNU pure and GNU const to somehow, you know, give a little bit of a hint as to what's going on. There are also actually warning levels. If you're worried that this is hurting you, you can do on GCC, it's W, I can't remember. If you search the documentation, there's a way of saying, hey, I spotted a function that's defined in a header file, declared in a header file, and I noticed that it's pure. If you annotate it as pure in the header file, maybe some other part of the code will benefit from it, but it's very noisy, as you'd imagine. It often doesn't matter. Speculative virtualization is a thing, and I'm sure that we're going to see a lot of new things coming from that. Linked TOM optimization, turn it on, find all the undefined behavior you've been unfortunately taking advantage of all this time, but fix them and then reap the benefits. The rest, the compiler can't save you from bad algorithms or bad data layouts. I'd like to thank the Compiler Explorer contributors, Ruben and Partouf, who's in the room, or was, and my Patreon supporters. Thank you very much for those that support. The images that have been in the background by a guy called Romain Guy. And of course, go read some assembly. Thank you very much.